Okay, so what we did before last week was we had dw prime dx square plus dw prime dg square plus L square of g and w prime equals to 0. Okay, and the Laplacian is already kind of written out like this. And L square of g is equals to n over u square minus ugg divided by u. Okay, like that. Okay, so and then if we take the one-sided Fourier transform, so f hat of k here, that's corresponding to w hat of k. Okay, kg equals to 1 over 2 pi integration of negative to positive infinity of w prime of k, not k, it's x and g. Okay, and then e to the minus I kx dx. Okay, so you make the Fourier transform like this. Okay, and so this one is pretty easy. This one we done last time. This one you just do it twice. You just do it twice integration, and then you make the integration by parts. Okay, and you should be able to do it. And then we reduce to 5.2.1. Okay, Fourier transform will give us w hat gg plus L square minus k square times w hat equals to 0. Okay, so this is the equation we're dealing with. Okay, 5.2.1. Okay, the Fourier transform of the linear low boundary condition will become this. Okay, this like. Okay, so Fourier transform is similar to that normal mode approach. So when you have Fourier transform of ddx, that's corresponding Fourier transform. Okay, to you take negative ik. Okay, similar to like you take it down. Okay, like before. And so your d square, the x square will corresponding to Fourier transform, will correspond to negative ik square that equals to negative k square. Okay. Yeah. Okay, so so a low boundary condition, we have w prime equals to u partial h partial x, okay, at g equals to 0. So then w hat, okay, you have to really give it a try to do integration, okay, but shortcut is this will give us, let me see, ik, okay. So, sorry, this probably give ik, okay, yeah, ik, so ik here, okay. And then this will give us ik, u, and then h hat, okay. So h is a function of x, right? So now h hat will be function of k. Okay, so this is at g equals to 0. That's a lower boundary condition. Okay, so then next we assume, make one more assumption. Okay, okay, our constant. Okay, so u, okay, g is equals to 0 or constant. So there's no shear or constant shear, then this term will be gone. Okay, so that means, okay, L square will be equals to constant Okay, and then this means we have second order differential equation with constant coefficients. Okay, for constant coefficient. Okay, of course k, you have different k's, but for each k is constant. Okay, and here we have a combination of many k's, but that is involved in the Fourier transform. Okay, but for each individual k, this is constant. Okay, and we have many k's. Okay, k. Okay, so here L is constant, so this constant coefficient. So then we can solve it. Okay, then the solution is like 5.2.3 A and B. Okay, everybody got this? Yeah. Kind of difficult to erase it. Let me try this one. It's probably not erase the problem. It's probably Marcus' problem. Yeah, I think it's Marcus' problem. Maybe the ink is too strong, so stick with it. Let me try using this one. Okay, so now once we solve it, then we have W hat. Oh, this is not good. I don't like this. This one is too strong. Oh, okay, good. Nice. Okay, so then we can solve this, right? Okay, so depend on L square is greater than K square or L square less than K square. We have two regimes, okay? So then we have 5.2.3A and 5.2.3B. So then we have W hat of Kg equals to W hat of K0 e to the I square root of L square minus K square times G. Okay, and W hat of Kg equals to W hat of K0 e to the minus I square root K square minus L square times G. Okay, for L square is less than K square. And this one is for L square greater than K square. Okay. Okay, now we can take the inverse Fourier transform. I think we did this before. We stopped here, I think, last week. So, okay, we take the inverse one-sided Fourier transform. Okay, and then we get this solution. I don't know. I will spend more time in erasing it than writing it. Ooh, I guess it's ink problem. Ink is going to stick too much into the board. Chang, do you do exercise in Taiwan? Maybe it's time for you to do exercise. No.
Save our time.
No. I'm just kidding. I'm just kidding.
Need some water.
No. We can.
It's much easier.
No. We can just. Okay. Okay. I'm just kidding. Okay. Yeah. See, it's ink problem. See, it's much easier here, right? Even stay there for over the weekend. So it's kind of. Okay, so it's gonna make it difficult. I guess I probably just erase it. Okay, I need to do some exercise myself. I tell you I don't like this kind of whiteboard. Okay, so we have these two solutions, and this is for k less than L, this is for k greater than L. Okay, and then we do the Fourier transform, okay, backward. So then if we do that, we have W prime of xg would be equals to the real part of, okay, 0 to infinity, and then W hat of kg. Okay, this is in the Fourier space, the function in Fourier space. Okay, and then we have e to the I kx dk. Okay, this is the one-sided Fourier transform. Okay, actually this is inverse. Okay, Fourier transform like this. Okay, and remember here we have the inverse Fourier transform defined this way. See here, 2 times real part of k goes from integrated from 0 to infinity, and then f hat of k, that's W hat of k. G stay there, G stay there, okay. And then e to the ikx dk, like this. Okay? Understand? Okay. Okay, now this one will break up into 2 parts. So this gives us the real part of, okay, 0. Since we go to integrate with k, so, okay, 0 to L, W hat of kg e to the ikx dk plus L to infinity, W hat of kg e to the ikx dk. Right. I can break up into 2 parts. Okay, 0 to L, L to infinity. Okay, this means, this part means what? Anybody knows what this part means? This part. This part means k is less than L. Right. Right. Because k integrated from 0 to L. This part means what? This part means k must be greater than L. Right. So this means k square greater than L square. This means, okay, this means k square less than L square. Okay. So these two have different solutions. Okay, one is here, one is here. Okay, so this part will be which solution will be this one, right? Right? No? Will be this one, right? Okay, the first part will be this one because that requires k squared less than L squared. So k squared less than L squared. Okay, so then we'll write the following: the part of 0 to L. Okay, this part will will be k squared less than L squared. So k squared less than square is this part. This part is this one. Okay. Yeah, so we have the head of k0 e to the I square root L square minus k square times g. Okay. And we have dk e. Then we have to multiply this e to the I kx dk. Okay. My writing is terrible. I don't like those markers. Yeah, cannot write very well. Okay, and then I used to write it is reasonable. We're looking. Okay, if I use chalk. Okay, have you guys seen chalks? Probably not. Yeah, probably not. Maybe too young. Okay, I believe you have seen chalks, right, in elementary school or middle school. Okay, and then second one is L to infinity, and this is the solution of this second part because it's k greater than L squared. We need k to be greater than L. Okay, so then we have this one will be second one, W head of k0 e to the minus I square root of k squared minus L squared times g, and then e to the I kx dk. Okay, so this will be our solution. xg. Okay, so this will be our solution. Okay, our solution. So to solve this is analytically is not that trivial. Okay, not easy. So, but there are three special, okay, kind of regimes we can solve. One is when k is much greater than L squared, and also when k squared much less than L squared. That's two extreme cases. And then other case is when k is almost equals to L. Then we can solve these three cases analytically. And otherwise, it will be difficult to make inverse Fourier transform. Very difficult. Okay, but this test is easier because you have the numerical model. You can just do it by numerical models. Okay. Also, you can do it analytically, semi-analytically, by using the first Fourier transform. You can do that too. Okay, that's almost like theoretical results. Okay, so now before we do that, we also have to consider the H head here. Let me see. WK. Okay, so here we also have to consider. Okay, we also have to consider. Oh, it's here. Yeah. Okay, so we also have to consider what is W head K0. Okay. Okay, W head K0 is W head. Okay, that's the vertical velocity in the Fourier space at g equals 0. That's the low boundary condition. Okay, so this is low boundary condition. Okay, this is low boundary condition. They are same. Okay, and actually I just derived it. Okay, so W head of K0, okay, that is equals to what? I think we just did it. Okay, we just did it. I think it's IK and then H head of K. Right. Okay, remember. This is low boundary condition. That's what we just had. See here? This is low boundary condition at g equals 0. And then W head of K, g equals 0, will be IKU, H head. That's this. Okay. So this 0 means, this means g at 0. Okay. At g equals 0. That's low boundary condition. Okay, now, H head, we also have to specify in order to get this solution. Okay, so it depends on your geometry of the mountain. Okay, so say if we use the, we assume the mountain is bear-shaped like this, bear-shaped like this. Okay, and HM is mountain height. A is the half width. Okay, because at that point, your mountain height is half of the mountain peak. Okay, that's HM over 2. That's called half width. Okay, and this one can be transformed in a simple form. That's why it's so famous, people use it. You also can use Gaussian if you want, okay? And you get this, okay? E to the minus Ka, okay, A is half width, HM A divided by 2, okay? So it's a simple form. So for bear-shaped mountain, okay, h hat of K is equals to HM, I don't like it, okay, divided by 2, e to the minus Ka, like that. Okay, so we can substitute into it. So this means, I don't like the writing terrible. Okay, W hat of K, so difficult to write with markers. K0 equals to, okay, then we have I K HM times A divided by 2 e to the minus Ka. Okay, so now we can substitute this into here, okay, and then we have the solution. Okay, so I assume you're done with this, so probably we can just replace this coefficient inside. Okay, so we can substitute into it. Okay, so we can move this into here. I K H sub M divided by A to the 2 e to the minus Ka. Okay, and we substitute this lower boundary condition into it for bear-shaped function, mountain. So then we have I K HM divided by times A divided by 2 e to the minus Ka. Okay, so for bear-shaped mountain, we have this solution. Okay. And by the way, some students, some of you may kind of question why you need to use, okay, kind of one-sided Fourier transform. Why don't you use the just regular Fourier transform? You can do that, okay. Okay, it's just for convenience because we are dealing with symmetrical mountain, and it's pretty easy for one-sided Fourier transform, okay. But you want, you can still use the regular one. Regular one is very similar to this, except here K is, you take absolute value, put negative there. Okay. And this bear-shaped, this kind of one-sided Fourier transform is pretty convenient for kind of positive K. Okay, assuming your K is positive. If regular Fourier transform, K could be positive or negative, then you have to take absolute value here, negative. Otherwise, it's identical. Okay, so if K is positive, this will become K, right? If K is negative, then this becomes negative, okay, Ka, okay, so absolute value. Okay, so this one will reduce to that for K greater than 0, okay. Okay, so now we substitute into it, okay. Okay, we can substitute into it, and okay, into it. Okay, so this one, okay, this one is IK, and then U times H hat of K. Okay, this one. Okay, this one. So I just kind of write it out. K U H hat of K. Okay, now this is the first case. L square much less than K square. Okay, and which regime is this? Yes.
We need to multiply 2 by the right-hand side of the solution.
This one?
The whole solution.
The whole solution.
Right-hand side. Because the equation on the analysis multiplied by 2.
Oh yeah, you are right. You are right. Yeah. So, yeah, we have to write. We have to. Yeah, thanks. We have to multiply by 2 here. Yeah, I forgot. Okay, thanks. Okay, so now if we have L square much less than K square, okay, so we have 2 parts of the solution. So if K square much greater than L square, K square much greater than L square, okay, so K, this one K is less than L square, okay. If K is much greater than L square, so which term will be gone? This term will be gone, right? Because this one, K is less than L, right? K goes from 0 to L. That means K is less than 0, okay. Then this term will be gone. So now we look at a special case, okay, kind of extreme case. Case 1, okay, if L square is much less than K square, that means AL much less than 1 or NA much less than U, okay. Because K is equals to 1 over A, okay, yeah, so when you have L square, this means, okay, L much less than K, assuming K is positive, okay, so we have this, okay, and K is equals to 1 over A, okay, 1 over A. So this means, okay, AL is much less than 1, okay. So AL much less than 1, I think we're done with this. Okay, so AL much less than 1. Okay, A is the head width of the mountain. Okay, here is HM, and here is negative A, is positive A. Okay, and L is N over U, less than 1. Okay, this means okay, NA much less than U. Okay, so head width times N much less than U. So, okay, no, we don't have to do this. Okay, we don't do this. So this means, okay, it's much less than 1. That this means implies physically, implies A is either or combined. Either A is much less than 1. What does that mean? Or small a. Small a, what means? That means narrow mountain. Narrow mountain, okay. Right. Okay, because you need this combination to be small, so A cannot be too big. So A is small. So narrow mountain. Okay. And N will be larger, very small too. What N small? That means weak stratification. Stratification. That means n is small or okay, larger u to make this whole term small. Okay, okay. So we need this, okay, and or okay, u is large. That means stronger wind, basic wind. These are physical meaning. Okay, u large. Okay. In other words, we need this term to be small. That means we need a to be small, n small, u large. Okay. And you can have one term enough to dominate, to make it much smaller, or you can have a combination of that situation there. Okay, that's physical meaning. Okay. So in that case, then this term, okay, will become this part. Okay. So let's say term A, and let's say this term B. Okay. So in this case, okay, this K must be less than L, so this greater. So this means term A is approaching 0, okay, because K in terms A, K is because K is less than L, okay. But that's another case because K must be greater than L, okay. So that means W prime of xg will be approximately equals to the last term, okay. So L to infinity ik u h hat, and then e to the minus I square root k square minus L square times g, and then e to the I kx dk. Right. We have equals to 2 times real part, like this. So that's a solution. Okay, that's a solution. Okay, for L square much less than k square. Okay, so term A got to become, right? Because term A doesn't even have k greater than L, like this. But since k is much greater than L, so this term approximately equals to 0 to infinity, approximately. Understand? Agree? Okay. Because k is much greater than L squared, so this L looks like very small. Okay. Okay, so that's why we have this solution here. Okay, we have this solution here. This is solution here, like this. Okay, and besides that, one more term can be simplified. This term can be simplified. Okay, so what this can be simplified to? Anybody knows? Under this situation, will become k. Okay, this term will become k. Okay, so this term will become k. So this term, okay, will approximately equals to k. So then our solution, okay, become minus I times kg here. Okay, so I guess you're probably done with this, right? Oh, I can write here. Okay, so the prime of xg can be written as 2 times real part. I probably just say equal, okay. And then integration from 0 to infinity. And this IKU, and then h hat is what? H hat is hm times a divided by 2 e to the minus ka. Okay, so this first part will be like this. Okay, so we'll have ik hm times a divided by 2, and then e to the minus ka. Okay, that's this whole, this part. Okay, this part, IKU, okay, h hat. Where is my u? I should have u there. I have u. I should have u. I should have u here. Okay, I should have u here. So I have u here. I should have u HMA times u here. U here. Okay, and then this one will become negative I times k times g, and then e to the ikx dk. Like this. Becomes simpler. Okay, yeah, simple. Okay, again, we can also use the eta. Okay, because eta is related to W prime by this equation. Eta is the vertical displacement. Okay, vertical displacement. Okay, so that it means at a certain height, okay, undisturbed height like 3 kilometers, and then eta will be up. Okay, up will be positive, down will be negative. So eta will be positive, negative. Okay, it's called vertical displacement. Just thinking about if we look at, say, 3 kilometer height, and then just think about this is the water surface, and then you up and down. Okay, apart eta will be vertical displacement from this 3 kilometer. Positive, down will be negative. Let's think about this. And then 5 kilometer, you also say this water surface at 5 kilometer, if you up and down, that's eta. Okay, vertical displacement. Okay, so then becomes simpler, and then we can kind of also use this, and we derived this earlier. Okay, so eta hat will be equal to W hat divided by IKU. Okay, so then we can have eta hat of xg equals to W hat of kg divided by IKU. Okay, and remember, inside part is W hat. Inside part is W hat. Okay, inside part. So okay, so inside part. Inside part, except this one. Inside part, this part is W hat of kg. Okay, and this is the inverse Fourier transform part, dk. Okay, so this is W hat. So if W hat, okay, that divided by IKU, so that means the eta xg will be equals to 2, and then real part of this integration of this divided by IKU. Okay, so IK is gone, U is gone. Then that gives us HM, okay, times A divided by 2, e to the minus Ka, e to the minus IKG, e to the IKX dk. Okay. And I think we have parentheses here. Okay, this is called the right square parentheses. Okay, where it is. Okay, now where k, we can combine together. Okay, so eta, so this eta of k xg be equals to, okay, real part of 0 to infinity of 2ahm. Okay, so we can pull that out. This can pull out, 2 cancel out. We have hm a. Okay, because they are real number, so we can pull it out. So then we have real part of 0 to infinity e to the okay, mass Ka e to the mass Ikg e to the Ikx dk. Okay. Okay, so let's take a break and come back probably 10 minutes later. Okay, let's continue. So, so this is equal to Hm times A, real part of 0 to infinity, e to the minus A plus G minus A minus A minus A minus X plus G, no, minus A, and then minus A plus, okay, we have K outside, K minus A plus Kg plus G Ig minus Ix rồi minus K Ig rồi, this Ig negative out, okay, and this will be K out will be minus Ix. So this is equals to e to the minus A minus I X minus G, okay, times K, like that, okay, and then dk. So this can be written as minus A minus I X minus G. It's changed, a little bit odd. Okay, but it's probably correct, like this. So then this can be solved. Okay, this can be solved. Okay, it can be solved. Okay, yeah, because this is this integration of e to the mass alpha k dk. And what's this? What's this? Forgot, right? What's e to the k dk? What is e to the x dx? E to the x, right? Right. Okay, and how about alpha? That'll be 1 over alpha, right? Alpha. Right. So this will be, okay, this will be, okay, this will be what? Okay, this will be 1 over alpha, and then e to the minus alpha k. Okay, yeah. Right, this negative alpha will be just alpha here, okay, like this. So then you can solve it, okay, you can have Hm times A, and then, okay, this will be what? Alpha, right? So then will be real part of, okay, so then will be negative 1 over alpha Okay, but alpha is -1. Alpha will be a minus I x minus g. Okay, e to the minus a minus I x minus g. Okay, and then you have your k here, and then k equals to 0 to infinity, like that. Okay. Okay. So that b equals to the part of -1 over a minus I x g. I have a feeling something wrong here. Okay. Some feeling wrong. I probably missed something. Okay. But I think the procedure is pretty straightforward. Okay, you do this. And this one, k equals to infinity. This is equal infinity. This e to the minus infinity. Okay. This is e to the minus infinity. Okay, when k goes infinity. So this term will be equals to what? Zero. Right. Right. Because this part e to the minus a minus I x minus g. Okay. And then times k, and then k equals to 0 to infinity. This means e to the minus a minus I x minus g, and then times infinity. Okay. And then minus e to the minus a minus I x minus g times 0. Okay. So this means this term is infinity. That means it's 1 over e to the infinity, and then minus e to the 0. Okay, this time 0. So this means it's equals to 0. This term is 0. So it's minus 1. Okay. So this term gives us minus 1. So minus 1 cancels out, plus. Okay, we have this. So that you can solve it. Okay, I guess something wrong here. Okay, I guess something wrong here. Something wrong there. Minus Ka, minus Kg. That's why. Minus Kg, minus K. I think there's something wrong there. Anybody find it? I can give you an extra point or 2. Can you find something wrong there? I think I missed something there. Okay. Yeah, I give you 1 minute so you can earn 1 point or 2 extra point. Yes. Say again. Yeah.
No exponential makes the I can be there is no I.
No I here. Okay. So you get 1 extra point. Okay. Can you keep record? Yeah. You will get 1 extra point. Yeah. Okay. Okay. So we don't have negative here. I here. No I here. Okay. So no I there. That means what? Yeah. Okay. I also feel like something changed there. Okay. So that means alpha will be what? We have no I. So here will be a plus g, right? A plus g minus x. Minus ix. You know how to solve this, right? Okay, you know how to solve this, right? Okay. Right, you know how to solve this, right? Do your part of this. Okay. So you have real of 1 a plus g minus ix, like this. Then this equals to real part of a plus g minus ix. You multiply by a plus g plus ix, a plus g plus ix. Okay. Then downstairs become positive, right? Become real number. So this becomes. I probably shouldn't go too detail about the mathematics, okay? Otherwise, we'll have no time to finish this class. Okay, what's this? What's here? A plus g squared, right? And then you have minus ix squared. Okay? And then you have a plus g plus ix. What's this? It's negative, cancel out. So this become plus x squared. Okay. Agree? Okay, and what's the real part of this function? What's the real part of this function? This will be equals to real part of a plus g squared plus x squared plus I of x a plus g squared plus x squared. Okay, so this is imaginary part should be gone. So then only this part left. Only this part left. X squared. Okay, so the solution will be hm times a and times a plus g and then a plus g square plus x square, like that. Okay, that's the solution. Eta of xg. Okay, let's check to see if the solution is correct or not. Okay, so let's check to see if this is correct. Everybody got this? Okay, so at g equals 0, what's eta? That's hm times a squared divided by s squared plus a squared. That's h of x. So that's correct, right? That's the mountain surface, the mountain geometry. So flow will be following the mountain at the g equals 0. That would be just the mountain geometry. Okay, that's correct. Okay, and you can see the disturbance eta is not exponentially decaying. But it decays based on this function. Okay, more or less kind of eta is proportional to 1 over g. Instead of before, Okay, before, when we have the sinusoid mountain, okay, it's proportional to e to the minus, okay, alpha g, something like this. Okay, that's the solution we had before. This is for kind of sinusoid mountain. So mountain, the disturbance reduced quickly, okay, to 0 by exponentially, but here it's just algebraically reduced, okay, with height. Okay, remember this solution we had it before. Okay, so okay, remember we have this this solution before. Sinusoid mountain. Very early. Oh, it's last chapter. Okay, it's coming question regimes. Okay, so 7.2. Okay, so here we have sinusoid mountain, and here we have pear-shaped mountain. Okay, and the solution, okay, are different. Okay, the basic, okay, things is correct, is not correct, is consistent, is, okay, we are in the evanescent flow regime. You have to know this, okay, because in the test, people will ask you, okay, if give you a solution, okay, it's an evanescent flow regime or it is vertically propagating wave. Okay, so now we are in evanescent because right now we have k square much greater than L square. Okay, so it's in evanescent flow regime now. Okay, so they both have the disturbance decay with height, but decay in a different rate. Okay, so we have this k square greater than L square, right? K square greater than L square here. Okay, so in this one is evanescent flow. So our solution is exponential decaying with height. That's our solution, decaying with height, exponential decaying. Now, we are also decaying with height. It's also evanescent flow, but at a different rate. It's A plus G divided by A plus G, so almost proportional to 1 over G. So this is almost eta proportional to 1 over G. Okay, so it's not decaying exponentially. Okay, but both are evanescent because both with the disturbance decaying with height, so we have the boundedness, upper boundary condition. Okay, so I think we have to speed up a little bit faster because otherwise we will never finish this class. Okay, and then you guys have to go to America to continue finish the class. Okay, that'll be fun, right? Go to America. The only problem is money. Okay, money. How do you say money? In Taiwan we say money, right? In America they say money. They use this money. Okay, yeah. Okay, I think in old time, but because in old time the money is okay in Tongban. Okay, so we say money, but they say this. Okay, so. Okay, so and the good thing about this way of discussion about mountain earth theory is we already understand. Okay, it's sinusoid mountain, and it is. We have two regimes. One is evanescent, one is vertical propagating wave, and then we understand that now we get more complication with isolated mountain, but then the basic dynamics is same as before. Okay, but solutions are different. Okay, you both are evanescent flow. Okay, both are decaying with height, the disturbance, but one is exponential decaying, and other one, this one, is decay at a smaller rate, 1 over G. Okay. And then now we can plot it out. Then like this one. Okay, decaying. Okay, looks like decaying is same thing, right? But it's isolated. Decaying kind of algebraically. Okay, 1 over G. And now, so the next regime is when L square much greater than K square. When L square much greater than K square, which term should be knocked out? Which term? When L square much greater than L square. We have to keep this term, right? Keep this one, right? Because L square greater than K square. This term will be gone because this term requires L square less than K square. So this will be gone. Okay. And then L square much greater than K square, so this will become IL. Okay. So become IL. Okay. And then that's right here. Okay. ILG is ILG. And okay, so solution become like this. Okay, then okay. Now if we plug H hat K, so H hat K is the H hat K, just a reminder to you, that's the phase transformed function of H. Okay, that is equals to Hm times A divided by 2 e to the minus Ka, like that. If we use the regular Fourier transform, that will be, okay, same thing, e to the minus K times A. Okay, yeah. Okay, and this is the kind of one-sided Fourier transform. This is regular Fourier transform. Okay, so we have this one. We substitute in there. Okay, so this H_K will be Hm times A divided by 2 times e to the minus Ka. Okay, this is H hat. H hat. Okay, 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 H hat times e to the minus Lg, like this. Again, we can combine this together. Okay, and then solve it. Right. We can combine these together. We can have negative IKA, and then these two we can combine because they both have I. So I times Kx plus Lg here. Okay. So this after substitute H hat, we get this Hm times A divided by 2 e to the minus Ka. So now, okay, all those okay coefficients, and then this one we can keep this one, and then these two we can combine together, e to the I of times Kx plus Lg. Okay, so we have this. Okay, and this one can be solved also. Okay, and become like this. So now we're X and G closed term here. So this term, this equation, this solution, okay, will repeat vertically, because in vertical we have sine function and cosine function. That means disturbance will repeat vertically. Of course, in real atmosphere we don't have disturbance go to infinity because we have the L square not constant. Okay, so some wave are reflected and some dissipated. Okay, because here we don't have dissipation. So this is a solution. And you plot out. Okay, you plot out, you'll find that like this one. Okay, so you have the vertically upstream phase tilt. You have upstream tilt with height. Here, this one, this here, and now you look at you look here. This is almost like mountain reversed. Okay, you look at here. It's almost like same as mountain because it's repeated. Okay, the wave energy can propagate to infinity. Okay, so wave is repeated. See here, repeated. Okay, and what's a repeat? What's the height of the repeat of this? Okay, this is called reverse mountain. Okay, this is repeated. So this is one wave, vertical wavelength of the mountain wave. Okay. So that's a solution for second part. I don't think I'm going to go detail of the math. Okay, probably let you guys do it. Okay, yeah, Yeah, they look as smiling, right? Okay, so I let you do that second one. I do one already, so I let you do the other one, okay? Okay, so we have the solution. The solution like this. Equals to, okay, this one is with a non-Buzynsk, the more realistic flow. Okay, so this is a solution we have. This is a solution we have. So eta HM times A, and then A times cosine LG minus X sine LG divided by S squared plus A squared. First, let's check to see the solution is correct or not. Okay, so to check it, one way to check it is to, there are many ways you can check it. One way to check it is to look at G equals 0. Then eta is supposed to be disturbance, right? But that disturbance of the flow supposed to be follow the mountain. So that's eta x G equals 0 equals to, what's this? Cosine 0. What's cosine 0? It's equals to 0, right? 1. Okay, so this is equals to 1. Sine 0 is equal to 0. So this term is gone. This is 1. So that is HM A. So this is become A, the A squared divided by X squared plus A squared. That's correct. Okay. So that's one simple way to check your solution is correct or not. Very simple way. Okay. Lower bound condition. Okay. Suppose that's what you assumed. Okay. It's no friction. So it's supposed to free slip. Okay. Follow the mountain. Okay. And second thing is, okay, so that's solution correct. So so flow, okay, follows the mountain. Okay, so this is consistent with the lower bound condition. Okay, second thing is, okay, the disturbance. Okay, can, okay, can go upward to infinity. Disturbance because we have sine LG and the cosine LG. Okay. And this is vertical propagating wave. And right now we are only in half plane. Okay, because lower boundary is solid. The only way to propagate vertically will be just up. Okay. Okay. And L is constant, so there's no reflection. So, okay, the disturbance go to infinity. The third, okay, the disturbance okay follows, okay, disturbance repeat, okay, itself vertically. Okay, And so you look at the solution, that's cosine sine function. It's going to repeat at what level it's going to repeat. If somebody asks you this question, what level is going to repeat? If we have sine function or cosine function, like, so say if we have sine function Lg, okay, so at g equals to 0, okay, it's going to be like this, right? At g equals 0, okay. And then, okay, but right now at g equals 0 is not sinusoidal, right? Because sine Lg is height. In horizontal, it's going to be like this, right? That's the pear-shaped mountain. Okay, at certain height, it's going to repeat this mountain. Which height is that? In vertical direction. Okay, so when we have this, okay, at a certain height, g equals to something, it's going to repeat mountain. Geometry, the mountain profile, it's going to repeat, okay. Like this, you can repeat. What height is this? When you have sine, okay, when you sine, say, Lg, okay, g equals to 0, sine Lg equals to 0, right? And what's the next level? The sine Lg is going to be also equal to 0. Will be 2 pi, right? Right. Sine function, you have 0, you have sine function, then you have 0, you have 2 pi, you have 4 pi, you have 8 pi, it's going to be equal to 0. That's okay. So Lg is equals to 2 pi, then it will repeat. If Lg equals to 2 pi, then this will be, okay, same as that. So that means G will be equals to 2 pi divided by L. What's L now? What's L? Come on, what's L? L is square root of n squared divided by u squared. So that's n over u. Okay. L, remember L squared is n squared over u squared minus ugg divided by u. Okay. We assume no shear or constant shear. Okay. Then we got this. So L is equals to n over u. Okay. So this means 2 pi divided by n times u. So at this height is going to repeat. And other height, okay, 4 pi u over n is going to repeat. So this will be equals to 2 pi u over n. Okay. So now, if somebody asks you, okay, you have u equals to 10 meters per second, you have n equals to say 0.01 per second, then what's the height is going to repeat? It will be 2 pi, that's 2 pi will be 2 times 3.14 times 10 divided by 0.01. What's this? Roughly speaking, what's this? That'll be 6.28, right? Okay, 6.28, okay, times, okay, 1,000. So that's 280 meters. That's 6.28 kilometers. So at this height, it's going to repeat. Okay, yeah. Repeat the mountain shape. Okay, the disturbance. And then other 6.28 will repeat. Okay, and that's why you see this repeating. That's why you see this repeating here. See here? Okay, so see, it is repeating about 12. There is about what? Okay, so this is a 12 is repeating. There is 6.8. So that means here its repeating rate is different. Okay, it's different. It's probably U. I think the U and N are different in that protein. Okay, but here, if say somebody asks you this question, then that's 6.828 is going to repeat the mountain shape. And other 6.28 is going to repeat again. Okay, so this is called vertical, okay, wavelength of the mountain wave. Okay, so this one, we call it, say, lambda, because this is called the vertical, okay, wavelength of the mountain wave. Okay, on the mountain waves. Okay, that's lambda 2 pi u over n. And we are talking about, so we repeat it, okay, vertically, with vertically disturbance repeats itself vertically, okay, itself vertically at a vertical wavelength of 2 pi u over n, like that. Okay, and we are talking about here L square much greater than K square. So that means n over u much greater than, okay, 1 over a. Okay, this means we have a over u much greater than 1 over n. Okay, and this is the 1 over n is the vertical oscillation. Okay, so or you can probably put 1 over n. You probably can multiply by 2 pi here, and then this will be the time period of vertical oscillation. So this will be buoyancy oscillation due to buoyancy force. N is due to buoyancy force. Okay, and this will be what? T of 2 pi times A. You know, A is not the whole length. A is only half width of the mountain. Okay, so 2 pi times A, that's the mountain scale. So this mountain scale divided by U, that's elevation. Okay, T of elevation. So the elevation time will take much longer time to, okay, compared to vertical oscillation. So mountain is wider. Okay, so take a longer time to pass over, and then the air parcel has changed to do vertical oscillation, and then produce mountain waves. Okay, so which regime is this? Vertical propagating wave, but extreme case, that's hydrostatic wave. So this is, okay, hydrostatic. Okay, so this is kind of hydrostatic. Probably I should say 0 here. Okay, so it's hydrostatic mountain wave. Okay, like this because, okay, we have L square much greater than K square. Okay, which give us this. Okay, which give us this. Okay, so then you have same phase tilt upstream because flow coming from left to right. See here? Phase tilt, phase tilt, phase tilt. Okay. Okay, so this is mountain wave. Okay, this is hydrostatic mountain wave. Okay, and phase tilt upstream. Okay, I probably also say additional characteristics is okay, the mountain wave. Okay, tilt upstream with height. Okay, so those are kind of characteristics of this hydrostatic mountain wave. Okay. This special case, L square much greater than K square. Okay, if we don't assume Buginisk, then our solution is very similar, except there's an extra term coefficient ahead of the original solution with the Buginisk solution. So we have this rho sub s divided by rho of g and take a square root here. And rho is the density of the air. So rho sub s is a density near the surface. Rho of g is at any height, like that. Okay. So for lung Buginisk fluid, that's more realistic, okay, fluid. Like atmosphere, okay, Buginisk is just a very simple, okay, make things more manageable, okay, mathematics more manageable, but also keep essential physical properties. And our atmosphere is more non-Buginisk fluid, okay, then our eta will be equals to square root of L, rho sub s divided by rho of g. Okay, probably I just say rho. Okay, I say rho here. And then the last part is same as before. Okay, A times A. This is for hydrostatic flow. That's for L square much greater than K square. Okay, and this is extreme case. This is kind of vertically propagating wave. Vertically propagating wave. And extreme case is hydrostatic. Okay, it's purely propagating vertically. Okay, and then cosine Lg minus sine times x Lg divided by L square, x squared plus s squared. Okay, so density is decreasing or increasing with height. Come on, you should know. Be more active, okay? Yeah, come on. Density is decreasing with height or increasing with height? Decrease with height. Normally decrease even exponentially with height, okay? And so that means, okay, this term will be greater than 1. That means wave can amplify with height, especially, okay, especially when you go to the stratosphere. In stratosphere, the that density, density become very small, so that can amplify too. Okay, so wave can be amplified, okay, if waves propagating to place with this dense fluid, they can amplify. Okay, and that's why some waves, you can see some waves in the troposphere, not very large, but it amplified in the stratosphere. It's because density there is much less than near the surface, so that can amplify. Okay, so 5 waves may amplify. Okay. And may amplify proportional to square root of rho sub s divided by rho. Okay, in non-Bouguenesque fluid. Okay. Okay, so this afternoon we are going to talk about when L square is approximately equals to K square. I guess I have to speed up a little bit, so I'm going to give you probably of more guidance of how do you approach to solve it. Okay, because it will take some time to do the math on the board. Then we're not going to be finishing this class. And of course, you guys are all welcome to go to America. Okay, the thing is you have to spend money. Okay, also you got to have time. Okay, you probably don't have time. Okay, right? Because you are going to take classes here. Okay, so we probably leave this as a homework. Yeah, write down this one and the previous one. Okay, this morning I have another one. Okay, yeah. So yeah, just kind of. Yeah, write down something simple so I can remind. So then, okay, yeah. So it's a good thing, right? Yeah. Congratulations. Yeah. So I find a lot of jobs for you to do. Okay, so then you can calculate this. This equals to pi over 4, and then rho naught times U times HM square. Okay, we have n, okay, here too. So we have n here, hm square. Okay, so this is for the case with L square much greater than K square. Okay, then you have this. If for L square less than K square, or even general case L square L square less than K square, then your drag will be equals to 0, like we did before without mountain. Okay. With the sinusoidal mountain. Okay, we have same thing too, except the values are different. Otherwise, the idea is the same. Okay, this also for L less than K. Okay, and this one too. Okay, also. Okay, also. Not same value. Also, okay, the drag is not equal to 0 for general case L greater than K. Okay, it doesn't have to be much greater or less than greater. Okay, but with much greater L square much greater than K square, then we can find a value easier. Okay, and okay, so now the third case. The third case, I probably will go quickly. Okay, a lot of math involved. Okay. Okay, so L square is approximately equals to K square. That means the advection, okay, of the air parcel, the effect is comparable to the vertical oscillation due to buoyancy force. So buoyancy forcing is comparable to the inertial forcing. Inertial forcing gives you advection. Okay. So then you For this one, it's more complicated. We have to look for asymptotic solutions. Okay. Okay, so now this is the, okay, this is solution. Okay, we discussed this morning. Okay, there are two parts. First part with k less than L, and second part with k greater than L. Okay, so these two parts, and this is because our k is no longer constant as before. Before, for sinusoidal mountain, we only have one k, one single k. But now we have many k's, okay, k, because okay, this is isolated mountain. Okay, and isolated mountain is composed by many waves with different wavelengths. Okay, so then we have to, and then this, if L is close to k squared, okay, then due to the kind of rapid oscillation of kx, okay, then according to Riemann-Lebesgue lemma, okay, it's called Riemann, and there are two scientists they propose this lemma. Okay, this Lebesgue. This is a French, and in French words, a lot of places S doesn't pronounce. Okay, doesn't pronounce. Like when you say Saint Louis, okay, it's correct, but a lot of people say Saint Louis. Okay, because Saint Louis, okay, was occupied by French, so a lot of people just say Saint Louis. Okay, and like there's a school they are very famous in, okay, basketball. It's called Louisville. Okay, and that's S doesn't pronounce. Okay, anyway, so like this, and so this one, okay, this whole term become 0. Why? Because this become very small. It's become very small, and then the e to the ikx, okay, oscillate, okay, fast. Okay, so then it's approaching 0. Okay, and Riemann-Lebesgue lemma. Okay, I have a quote here. Okay. Okay, that is when you have function which is smooth, that means it's ordinary and absolutely integrable. Okay, that's called smooth function. Then this kind of function, okay, then the integration will approach 0. Okay, so that can apply here too. Okay, apply here too. Okay, when you have L, okay, it's comparable to k, this term becomes small. Okay, this term becomes small, and then e to the ikx will dominate. Then you have rapid oscillation, then that, okay, will approach 0. Okay, so for, what I mean is, when that, what I mean is when this x is large. So when you talk about this, it's only apply when this. Let me probably give a little bit explanation. Otherwise, you probably cannot understand. So, okay, e to the ikx, okay, is equals to cosine kx plus I sine kx. Okay, so for, okay, large x, very large x, far away from the mountain, okay, then this kx is very large, okay, for very large x. Kx is very large. Okay, that means it's kind of oscillate very fast. Okay, understand? Okay, just take a look at sine x and sine 10x. Let's look at this. Then what is the oscillation period here? Will be 2 pi. Right, will be 2 pi. Right. And here will be 2 pi divided by 10. Okay, so the oscillation period is very fast. Okay, and then once very fast, and provided the function is smooth. Okay, that's this part of the function. That's this part of function is smooth. Then for large x, in other words, we are looking for asymptotic solutions, not near the mountain, will be far away from the mountain. Okay, and then we can get the solution. So then it will disappear. Okay, and okay, so now that's the Riemann-Becker lemma. Okay, now let's look at here. So if we look at for large x, we look at eta approximately equals to okay, the real 2 times real part of this one. Okay, and this one phi of k, we combine this together. Okay, we combine this together. Okay, so okay, so so for example, look at the first term 1. Okay, then we have 2 times real, and then integration 0 to L, and then IKU. Okay, times h hat of k. Okay, and then e to the I, and then we can combine them together. We can combine them together. Okay, so we have square root L square minus k square times g plus plus x times k, like this. Okay, so okay, see, okay, can I see? Yeah, and then kx here. Okay, like this. Okay, so if we call this as phi, okay, of k, then this will reduce to the following. Okay, we reduce to the following. Okay, so then we have h hat of k times e to the ikx. Okay. Okay, we have this, and then phi of k will be equal to square root of L square minus k square plus kx. Okay, and now this is called phase function because it's a phase. Okay, it's a phase function. Okay, this is a kind of phase function. Phase function. Okay, and this is called phase, right? So this is a phase function. And based on the stationary phase method, we look for a particular k star, okay, and then define the k equal 0. At that point, it's not going to oscillate quickly, okay, and this point is called the point of stationary phase. Okay, and then so for large x or g, then e to the I phi will oscillate rapidly. Okay, therefore eta will approach 0 according to. However, near k star, okay, the contribution to integration by e to the I phi remains. So you can get solution. Okay, so if you are just look at the Dutch X or Dutch G, then this kind of oscillate quickly. Okay, but except at that point, okay, then you are not going to get okay, 0. Okay, at this point. Okay, so try to read this kind of carefully. Your questions come to me. Okay, I explain that to you. Okay, so then we have this inference function. Okay, so G over X equals to this. Okay, when it's when equals to 0, the phi decay. So this is phi is the phase function, square root L square minus K square times G plus Kx. Now, if this decay the phi decay equals to 0, okay, at certain K, this certain K we call K star, and then this is called point of stationary function, okay, phase. Then, so what we need to do is to find this place. So we have d phi decay. So d phi decay equals to, we take this, okay, so we have the decay of square root L square minus K square, and then times G, where G is independent of K. So you can pull out, and this one become, okay, d phi decay and become X. Okay, so then what's this? Can you remember how to do differentiation? What's this? What's decay square root L square minus K square? That will be equals to the decay of L square minus K square, and then half, right? So that will be half of what? Of L square minus K square minus 1, so minus half, right? And then the decay of L square minus K square. Okay, L is constant. So this will become negative 2K. Okay, so here this will become, okay, negative cancel. This go to 0, right? This first term goes 0. So then we are negative, and then 2K, and then decay. Okay, so that's it. So then we have negative L square minus K square minus half, okay, and then times K. Okay, so that is equals to negative K, and then square root of L square minus K square. Okay, so that means the phi decay equals to negative K over square root L square minus K square and times G, okay, plus X equals to 0. We want it to equal 0 because at that point you don't have the strong oscillation. Okay, and then so this will give us that will give us this G over X. Okay, G over X equals to L square minus K square. Okay, so this one will give us the following. Okay, so that means we have G equals to square root L square minus K square divided by K times X. And then we call this K star. We call it K star, okay? That, at that place, we call it K star, that K. Okay, so K star is called K star is called K star is called the point of stationary phase. Okay, so at that point, okay, the oscillation cancel out by this at this place, because at this place that means at this place that means K phi, the phase function is not okay, is independent of k. So then you are not going to have strong oscillation, and that's called stationary phase. And then we have solution asymptotically. Okay, so then you can solve that. Actually, that's also a good problem to work on for homework. But I'm done already, so yeah. Okay, so then then we can have stationary phase. And then you take the Taylor series expansion. Taylor series expansion of phi of k near k star. Okay, I believe you still remember how to do this. Okay, Taylor series expansion, you got this, right? Remember we have this Taylor series expansion of of f of say x will be equals to f of x0, okay, plus f prime of x, okay, 0, and then you have x minus x0, and then plus 1 of 2 factorial at double prime x0, and then x minus x0 square, and then plus higher order terms. Okay, like that. And then so now you replace f by phi, and then x naught is k star, then you get that function. But this term is 0, right? Because partial square phi, partial k square, okay, is equals to partial k, partial phi, partial k. But this is equal to 0 at, okay, near k star. Okay, actually I should say at k star. Okay, but near k star this will be 0. That's what we want for this. Okay, this equals to 0. Okay, this equals to 0. Okay, so this is second term is gone. So then that means phi of k can be approximate by this term and this term. Okay, because it's 0. Okay, and higher order terms also 0 too, because of that partial phi partial k equal 0 at that point of stationary phase k star. Okay, then you can substitute this into there, and then eventually you get this. Okay, you get this. So, and then for Beer-shaped function, mountain h hat is equals to hm times a divided by 2, and then e to the minus ka. Okay, so then you can substitute in and you can get a solution. Okay, so this solution is along, okay, this is far from the mountain, okay, a little bit far, okay, and also up higher and away from the mountain, okay. So that gives us the asymptotic solution. And then you can plot it up, okay, and you can find k star equals to this for the Beer-shaped mountain. And then you can plot it, okay, you can plot this, okay. So now you can see this, you can see first tilt, see here, you can see first tilt that represent the upward propagating wave. So whenever you see the upstream first tilt, that kind of related, more or less has pretty good chance related to upward propagating wave. But also you see this part, okay, this part is coming from the, okay, non-hydrostatic part, okay. Okay, and then you also can plot the p prime, okay, and the u prime, okay, like this. They are related, just opposite to each other, p prime and, okay, and u prime. Remember we said this p prime is opposite, is proportional to negative e prime due to Bernoulli equation and also due to the momentum equation. And so you can plot it there and just have different scale, u prime and p prime, but they are same, they can be plotted as one curve. Okay, so, and this kind of argument actually is also related to the group velocity argument. Okay, so say if we have this group velocity, okay, this group velocity, this is omega. We calculated this before, and if we look at the group velocity in the frame of reference of the mountain, then we have u plus the omega plus k. So basically what you have here is simple way to say, without confuse you, is so say if we have a free wave without mountain, okay, then omega equals to u and k, and then square root of k square plus m square. Okay, so then suppose you have this, then your group velocity of E C gx will be d omega dk, and cgm, okay, not m, cgg, the vertical group velocity will be equals to d omega dm. M is vertical wave number, k is horizontal wave number. So we have this, okay. And now with the mean flow coming in and fixed in mountain, then you just have the u add to this part, okay. That means horizontal group velocity is like this without mountain, okay, without fixed with mountain, okay, and then with, okay, with the u, then the u coming in just advert the group velocity like this. So say if you have a group velocity cgx, okay, and then you are writing with a wave, then you don't have u. Okay, now if you are fixed with a mountain, then you just add u to it. That's all. Okay, so don't be scared by that. And then in g direction will be partial omega partial m times k. Okay, so this is for free wave, and then plus u is because u. Okay, you are in that fixed frame reference with mountain. Okay, so then, okay, so and then if you have the group velocity will carry the energy, then will be beside its own propagation is also advected by basic wind. That's all. Okay. Okay, then so say if we choose this omega you can choose positive or negative. Okay, so we are more interested in negative one. Okay, because here you can have positive and negative one. Okay, and this is not okay. This one, but we are more interested in this one because why? This one will be advected away, and this one has changed to be balanced with the basic wind. Okay, so you can have cgx. This is negative. This is positive. Positive will be carrying the energy downstream. Okay, if we have the basic wind, will carry downstream, and here the wind coming in can balance, u coming in can balance this. Okay, so then that will give us the stationary wave. Okay, steady state wave. Okay, and that one will be just advected out. Okay, doesn't mean it's not there. It's just once you produced, it will be advected out. Okay, so that's why we choose negative. And then once you choose that, then you can calculate the group velocity. And m means is with respect to the mountain frame of reference. Okay, then you got this. Okay, in I direction, in k direction. So in horizontal direction, in vertical direction, then you have this. Okay, and then you can calculate. You require if you require stationary wave, then that means your wave will be time independent. Okay, that means if you wanted to see wave here, that means your phase speed has to be equals to u. Okay, so then you can see okay, kind of stationary wave. And that's what we are looking for. Because we are not starting the transient wave or time-dependent wave, we are starting the steady-state wave. So U, okay, has to be balanced by Cpx. Okay, so U is equals to Cpx. And the Cpx you can calculate, right? Because that is, anybody remember what's the Cpx? The phase speed in x direction. Do you know how to calculate? It's omega divided by k. Okay, yeah. So then you have U equals to omega divided by k. Okay, so then you can get that U there, okay? Okay, so bottom line is, okay, this will give you a pretty good picture, even though if you are a little bit away from the math, at least you can understand this one, okay? So here, relative to the air, you got the good velocity, okay, propagate like this, okay, good velocity propagate like this, okay, and then U wind advect this group velocity, the energy this way, and the energy go this way, but then because we have basic wind coming in, so then eventually you see the group velocity going this way, and then you see wave, okay, here. Okay, and you have some stationary wave here, okay, because Cpx equals to U, okay, they kind of imbalance. Okay, but you can see the wave here, but also the good velocity, the energy, okay, is advected to here. Okay, originally it's advected this way, okay, propagate this way, but then being advected by mean wind, and then so you can see the wave energy here, but you can see waves here. Okay. Okay, well, you can see wave here is because of phase speed. Phase speed give you can see the wave. And good velocity is the place, the energy propagation, okay, direction. And so you can find the, okay, wave energy kind of propagate to here. But the wave, okay, you can still see wave here as long as Cpx is balanced by U. Okay, and then you can calculate CGG divided by CGX, okay, the good velocity in vertical direction divided by, okay, the horizontal direction equals to, okay, you can calculate this, and actually you can derive it equals to G over X. Okay, what's G over X? What's G over X? That's this. That's this. Okay, that's it. G over X. G over X. Okay. So G over X, that's good velocity. Okay. That's equals to the vertical component of CG. So here CGM, that's your vertical component, CGG divided by CGX. And that's just equals to this, okay, G over X. So you can explain this by also good velocity, okay, argument. Okay, so we are done, okay, of 7.3. Now next thing is we always assume, up to this point, we also assume the L is constant. And can somebody tell me what's L? What's L? Scalar parameter. That's very good. So we have where L square equals to n square over U square minus U G divided by U. Okay, so this in general is functional G. Okay, and okay, when you have no shear this term, okay, or shear constant, this term is gone. Okay, and sometimes in general, when you have this, if the variation is large, normally it's difficult to find, almost impossible to find the analytical solution. Okay, but if it's varying slowly, okay, with height, if this okay, very slowly. With height. Okay, then we can come up some solution. Okay, kind of partial solution, but that helps us to understand the dynamics. Okay, so again, we go to this scalar. Okay, go to this scalar equation in the Fourier space. We have W hat GG plus L square minus K square. Okay, and then W hat equals 0. Now, L square is no longer constant. Okay, so we no longer can apply easily. Okay, except if this is kind of varying slowly with height, then this is, you can approximately say it's almost constant. Okay, but not exactly. So the treatment is different. Okay, you cannot solve it as before. So this is no longer constant. Okay, so that means, remember before, we have solution of W equals to like, you see, we have W equals to, say, A e to the I square root L square minus K square, G plus B e to the minus I square root, okay, G, okay, or see like a K square less than L square, and then W hat equals to C e to the plus square root of K square minus L square times G, and then plus D, okay, e to the negative square root of K square minus L square. This is L square minus K square times G, okay, for K square greater than L square. Okay, now we no longer can do this. Okay, A, B, C, and D are constant. Okay, with respect to the height. Okay, we no longer can do that, but we can roughly say we have the solution in the form of the following: W hat of Kg equals to A, okay, and then Kg e to the I phi of Kg. Okay, in other words, our solution, if we have solution, we don't know yet. If we have solution, our coefficient will no longer, like here, independent of height. We have to include in height in here. So both, we have height here. Okay, and phi is, okay, so phi is the slow variant phase function. Okay, phi. Okay, so then we have to find this, this kind of solution, and then you can substitute this into 5.2.1. Okay, you can substitute into there and get 5.2.28. Okay, you can substitute there, and so we no longer have this kind of solution because they are constant coefficients. Second order differential equation, constant coefficient. We no longer have that. That's why A, the coefficient, is function of K as well as G. And here, A, B, C, D are only function of K. Okay, and here is function of K and G. So then, if we assume we have solution like this, and then we substitute into there, then when we have W, the W hat square dg square, okay, and that equals to ddg of partial W hat partial G, okay, and then here we have two terms, okay, we have two terms. That gives us partial G of, okay, A, and then partial D is I phi, okay, and then d phi dg, right? Because it's function of g, okay, plus dA partial A partial G, and then e to the I phi. Okay, so this gives us partial G of I A, and then phi, and then phi G. Okay, this is phi G. We write this way, and then we have AG, and then e to the I phi, like this. And then you can do the second time. Okay, just get more complicated because A, phi, and G are all functional G. So these become 1, 2, 3 terms. And here, this functional G, this functional G, so you have 2 terms here. So then it becomes 1, 2, 3, 4, 5 terms. And then I don't think it's very difficult. It's kind of very simple algebra. Okay, you come together, and then eventually you got equals to this. Okay, you can equals to this. Okay, we assume the variation of phi is very small, okay, or variation of L is very small, and that gives you variation of phi very small, variation of A very small with height. Okay, if it's very small, that means the phi, that means the square A, the G square is very small. Very small. Okay. Because it takes twice of the the differentiation. Okay. So that means this term becomes very small. So if this term becomes very small, what's going to happen? Then we have a real part here, we have imaginary part. And then individually, they are going to be equal to 0. Okay, we require it because we have real part and imaginary part equal to 0. Okay, and then individually, they have to be equal to 0. Okay, that's a complex number. Okay, so then in that case, we'll have the first part will be equals to minus A, okay, phi G square plus L square minus K square, and then we have A here equals to 0. And then second part, also this equal 0, okay, because of I. Okay, there's no way you can have these two equal to 0 unless individual part is equal to 0. So then second one will be A phi GG plus 2A sub G, that's partial A partial G, and then times phi G equals to 0. Okay. Okay, so we are going to stay here and take a 10-minute break. Okay, so I see you in 10 minutes. Okay, thanks. Okay, so now TTG equals this. Okay, what does this mean? TTG of this equals 0. What does that mean? What does that mean? This means this is not function of G, right? Okay, if this equal, if partial g equals 0, that means this is constant in terms of g. Okay, so it's not function of g. So that means a square times L square minus k square is equals to constant. Okay. Okay. With respect to g. Okay, we have this. Okay. So what does that mean? A is amplitude. Okay. That means if this is become small, if this is become small, then A is going to become, okay, larger. Right, in order to multiply together to be constant. Okay, so, but this means wave amplitude. So wave amplitude is become large, that's amplification, when this term becomes small. Okay, but what's this term? This term is square root of n square over u square. Okay, and then so this term actually, this become a square times square root of L square is what? L square is n square over u square minus what? UGG divided by u and minus k square. Okay. So is equals to constant. What does that mean? This means we are interested when A can become large, because we are not interested wave is going to dissipate or become small. We are interested in wave amplitude become large. Okay, and that's because A become large. Okay, A become large is when this becomes small. Okay, this becomes small. So when this becomes small is when you have n. Okay, so you want this term to be small. That means n is to be small. Okay, and u to be large. Okay, and UGG to be what? You want this whole term to be small, then UG got to be large too. Okay, so UG got to be large. Okay, so those are places wave can amplify. Okay, so when the wave propagate vertically to a place, you have weak certification. Okay, weaker certification. Okay, that means, remember, n square is equals to g over theta, this theta dg. Okay, so weak certification. Then, okay, then wave can amplify. And also, if wave propagate to, okay, to a strong wind region, like a jet streak. So say if, okay, see a mountain here, where wave propagate to a place we have the jet streak or jet, okay, like a jet stream or jet streak. Okay, jet streak is like a jet stream, but with localized maximum wind. That's called jet streak. Then if wave propagate to there, will amplify. Okay, if we have jet stream, like at 300 millibar or 200 millibar or 250 millibar, depending on where you are, then wave propagate to the jet stream. or just streak, it can amplify. Okay, so now we know there are different reasons wave can amplify. Okay, one is like we discussed this morning. Okay, here W prime equals to square root rho s divided by rho, and then you have the other terms. So when you wave propagate to a place, you have kind of smaller density, wave can amplify. Wave propagate a place which you have weak certification. You can amplify. Wave propagate to large U, like jet stream or jet streak, wave can amplify. So see, we have 1, 2, 3 mechanism wave can amplify. And we also know nonlinearity can make wave amplify. And then, okay, then steepening and then overturns. Okay, so now you have 4 mechanisms. Okay, and make sure you take a note. Okay, which can make wave amplify. Let me repeat. One is, okay, wave propagate to a place, the density become smaller area. Okay, which lighter fluid can amplify. Okay, that makes sense, right? The wave come to an area which, okay, is less dense. Then this dense is easier to, okay, to make it buoyancy force larger, okay, to amplify. And nonlinearity, okay, so, okay, to lighter, okay, or less dense region, okay, the wave can amplify. So now you have, first you have the nonlinearity. Remember that we have wave like this, and then that can overturns, steepening, okay, because of nonlinearity. So it can amplify too. And then second one, if wave propagate to less dense region, it can amplify, okay. And wave go to this can amplify, can go this amplify, or you can have strong shear, you can amplify too, okay. So 3, 4, okay. And 5.
How about a case wave?
Case wavelength, yeah.
So there's no any difference?
No, yeah, no. Case, yeah, wavelength, yeah, no, yeah, yeah. Okay, so here already, okay, I can discuss, okay, so combining with this will be constant, okay. So, maybe we have to, yeah, you're right, maybe we have to be careful. Okay, we have to assume K squared is much less than L squared, so this term can be ignored. So we can have this argument. And so these are for, okay, kind of for, when you assume this, that means it's kind of long wave, okay, or kind of hydrostatic wave. Okay, wave. Okay, so those amplification mechanism, okay, keep in mind. Okay, now you learned mountain meteorology. Okay, those are important concepts. Okay, you may forget some details of the mathematical manipulation, but those important concepts you have to keep in mind. Okay, so the amplitude of the vertical velocity increases. That's wave amplitude. Okay, significantly in regions of weak certification. That's n squared. Okay, and or strong wind. Okay. So like you have wave propagate to jet stream or jet streak. Okay, and then its amplitude can increase. Okay, so now here keep in mind this is important. Okay, conclusion based on 5.2.3 and previous discussions, wave may amplify in certain layers due to weak certification, that n square, small, strong wind, that U large, okay, it's U large here, okay, and nonlinear steepening, okay, that wave can, okay, nonlinear steepening, and abrupt decrease in mean density, okay, like this. Okay, so those are mechanisms which may amplify the wave. Okay, next topic is trapped D waves. Okay, I think I've shown this before. Okay, D waves, and like a schematic for the D waves and the rotors, like this. Okay, so wave can have like this. So you can see wave repeating horizontally. Okay, horizontally repeating like this, and then in a certain layer. And now, if this air parcel go up, if the flow is moist, and then the air parcel going up to LCL, then you can get saturated and form cloud. And then you'll see this part of the wave has clouds, okay? Then you see this part of the wave has clouds. And now, from shear right, you can see it, okay? You can see this wave cloud is lined up parallel to the mountain range, okay? So like this, and then you have, so you see like mountain like this, you see, and then if this is LCL, this part will be saturated, you're saturated. So you have cloud line parallel to the mountain, cloud line parallel to the mountain, and one by one. And that's what you see, we call trapped D waves, because on this side of the wave, okay. I don't know if you can get to it. Oh no. Yes. I say yes. Where is yes? Oh no, I don't want anything to do it. Okay, I just.
We can make it.
Huh?
We can make it just one and cross.
How do I do it? Bottom one. Oh, it's all right. One second. Okay. Yeah, I probably shouldn't touch it. Okay. Okay. Oh, that's fine. Yeah, you'll find it. Okay. I just say around. Then you can go to it. So I have some linked. Okay, you can see it a lot of kind of conceptual ones, and also there are some real ones. Those are real ones. Okay. Okay, real ones. Those are not real D waves. Those are real waves. D waves. Okay. And yeah, this D waves. But this is ship waves, okay, ship waves. Okay, so there are a lot of them, you can go there. Okay, so I have some links in the note, you can do it. Okay, this type of waves differs from the dispersive tails in figure 5.4, okay, that we showed this morning. Okay, it's called and it's because of resonance. Okay, so I go quickly because I think we don't have time to go details of this mathematics, okay. But since you already have the note, so you can read into it, your questions, you can contact me. Even after when I go back to the stage, you can still contact me your questions, okay? So, okay, so now we go back to the original scalar equation. Okay, so scalar equation like 5.2.1, okay, over there. that's W hat GG plus L square minus K square. That's W hat equals to 0. Okay. And then now we are to there. To there, so this is G, right? And we have, remember, assuming we have this, like this is L1, okay, and this is L2, like that. And if our K is in between this, then, okay, so K is less than L1, greater than L2, then we can have wave reflected, wave can reflect it, okay. And this level is called, what kind of level? What kind of level? Critical. And people agree? Yeah? Agree? Agree? I'm going to take your 1 point off. It's called reflection level. Remember that? So, okay, in that time we don't have the forcing, and now we have forcing. So it's good, okay, because we discussed that first. Now you have idea about what's, okay, we have this. Now, we have already have that kind of discussion about reflection, but without, it's called free wave without friction, without forcing. Now, if we put mountain in, okay, we put a mountain in, and then we have flow coming in, okay, then see what happens, okay. Okay, so now we have already have the background, okay. So now, this, okay, this become, okay, two equations, okay, and just follow what we did before. We have two equations. So then we have, in low there, we have L1, okay, minus K square, okay, because L1 is greater than K square. And in the upper layer, we have K square minus L2 square because K is greater than L2. So that is 2. And one thing different from before is for convenience, okay. You can still stick with it, okay, in that, okay, original approach, but right now we just shift, very small shift for convenience. We just set, before we set this H, right, we just set this as this one, G, we just set G equals 0 here, okay, and this will be G equals to negative H, okay, that's all, okay, so we just change that, and that gives us some convenience in mathematics, that's about it, okay. The basic dynamics is the same, okay, if you want, you can still stick with original coordinates, this is 0, this H, okay, but now we set 0 here and negative H. So now we have these two, okay, equations, governing equations. And then we can solve it actually, okay. We can solve it actually, we become eta 1 hat equals to kg, okay, equal this. We can apply the low bunch condition, okay, and we can, sorry, this is kind of free waves, okay, we can have these free waves. And then mu is, we just define mu as square root of L1 square minus K square, and then lambda equals to K square minus lambda, sorry, L2 square. Square, okay, like that. Okay, and then on top, okay, this is evanescent flow. Okay, flow, and okay, in that low layer, it is vertically propagating flow regime. Propagating flow regime. So we have two regimes here. And this one requires wave is not going to amplify with height because the source of the energy is here. So that means we are going to have this C times negative lambda G, and then we knock out the positive lambda g term. Okay, we have two solutions here, two terms here. Okay, so for 5.2.34b, okay, we have eta hat of layer 2 of kg equals to c e to the minus lambda g plus d e to the lambda g. Okay, because of boundedness, this one is increased, amplitude increases with height. Exponentially, that's unphysical. Okay, so this is because of upper boundary condition. Okay, which call upper boundedness. Okay, condition. So we can know that. And then lower there, okay, we can solve it. Okay, we can have that. And C, okay, so we have C is going to determine by what? C is going to determine by what? The coefficient C here. C by, remember this is partial differential equation, we have 2, okay, and that C will be determined by the, okay, by the lower boundary condition here. It says here, nobody read it. I gave the solution here already, answer here, okay, boundary condition. Okay, the upper boundary condition already applied, okay, so we knock out e to the lambda g, okay, because we cannot have amplitude increase with height, okay, because the source of energy is here, so amplitude should be smaller and smaller, okay. This is just like if there's a group of people here, group of people there, and you try to push them, okay, a lot of people, try to push them, people close to you will have more vibration, right? And then people far away will be less influenced. Okay, that's boundedness condition. You cannot have, okay, push here, and then there is kind of have a dot of amplitude, okay, kind of dot of vibration. Okay, so anyway, those we have discussed before, okay. And then now, so you can substitute that, okay, lower boundary condition, because now apply to g equals to mass h. Okay, the mountain is at g equals to mass h. We substitute that in, okay, and that is the boundary condition we have, right? Eta equals to h hat. Okay, remember eta is the perturbation at surface, and that should be following the mountain because it's free slip. Okay, so it should follow the mountain. And so then you substitute that, then you can solve this solution. And then you may have a little bit hard time to solve that. Okay, okay. You can also give the bear shape function, and then transform into the Fourier space. So h hat will be equals to, if bear shape will be hm times a divided by 2 e to the negative ka. Okay, so then you can substitute, and then you can try to solve it. You may have a little bit hard time to solve, okay, but you can apply a numerical method to solve it. Okay, so you can solve the solution. Okay, and now I want you to think about it. Mathematically, there's a problem. There's one place has a problem. Okay, look at that integration, that equation, the solution. There's a little bit problem. Okay, in general, no problem. In general, you can solve it. Okay, but there's a place, there's a problem. I give you 2 points if you can answer correctly. So look at that equation. Okay, there's a place, there's a problem. You cannot solve it mathematically. I give you a hint. Look at here. How many people are online? 5? Okay. So it's not quite a steady state yet. Okay. So here, look at this one. Look at here. If downstairs, the denominator, okay, is equal to 0, we have a problem. Right, we have a problem. Right. Because if 0, that is we call mathematically we call singularity, then we have a problem. But that singularity is very important physically. If this equals 0, that is the place you have wave resonance. Okay, resonance. Okay, that means because the wave can go up in low air and then reflect back, and then at ground will reflect back. You can have like reflection like this. Okay, so now if say somebody, maybe not me, okay, maybe a giant, okay, lift him up and down, okay, then he's going up and down, right? But then also there's wave go up and down. You have to be in phase to have kind of more or less kind of steady state oscillation. Okay, if your wave going up and coming down, if they're out of phase, okay, then you don't have resonance. Well, you know resonance, right? 共鸣. Okay, you cannot have 共鸣. Okay, so 共鸣 that means your phase are in phase. So going up, okay, or going down, reflect back with or going up, they are in phase. Then you can have resonance. Okay, that gives you these, okay, D waves, trapped D waves. Okay, and if not, you still have wave diffraction, but it's not maximum wave diffraction. Okay, but when you are in phase, okay, like if I push somebody, like push you, okay, if I push you and then you come back, I push you, okay, you come back, I push you, then that's 共鸣. Okay, if I push you and you come back, okay, I don't, okay, when you just come back, okay, I push it, then you still eventually will go back, but will be not maximum. Okay, so you come back, and when you are about to go back, I push you. Okay, and I push you. That's 共鸣, that's resonance. So that resonance gives us D waves. Okay, otherwise you can still have diffraction. You can still see waves, but not maximum. Okay, response. So how do you do it? Okay, you make this equal to 0. Make the downstairs the denominator. So you make cosine, okay, mu h plus lambda over mu sine mu h equals to 0. Okay, so that means your cosine mu h equals to negative lambda mu and sine mu h, and then that means cosine mu h divided by sine mu h equals to negative lambda g, lambda u. Okay, and what's this? What's this? Cotangent mu h equals to lambda over mu. Okay, and lambda and mu are kind of defined earlier. Lambda is square root of, I think it's k square minus l square, and mu is l square minus k square. Okay, so these are conditions you can have the wave resonance, and that gives us trapped D waves. Okay, like this. Lambda over mu, cotangent mu h. Okay, like that. Okay, and the resonance wave number kr star may be obtained by solving the above equation, either numerically or graphically, because that means kind of analytically it's difficult. You cannot have a coarse form, but you can do it by numerical calculation of this equation in above. And the criterion for existence of one or more resonance waves is like this: L1 square minus L2 square much greater than, not much greater than or equal to pi square over 4h square. So there's a criteria which you can have the resonance, the chirp waves is this criterion. In other words, your low level L1 must be greater than upper level. So say because L square is equals to what? Is equals to n square over u square, minus UGG minus u. So assuming there's no shear, so say we constant wind with height. This assume, of course you can have that to have the condition met, but assuming we have uniform wind, and then assuming we have like this n, this n1, this n2, like this. So that means L1 must be greater than L2. So your n, n must be greater than n2 at least this value, pi square over 4h square. H is the depth of this low layer which have stronger certification. So in other words, low layer it should be much stronger certification stratified compared to upper layer. And you can also have resonance waves of the nth mode, more complicated by this, more resonance waves, so like this. So conclusion here is, in order to have resonance or D waves, the scalar parameter is in the lower layer must be much larger than that in the upper layer. In other words, the lower layer must be more stable or with a much slower wind. You can also have stronger wind to get the larger air. Lower layer, L must be much larger than upper layer. So you can have either this one more stable or you can weaker wind. You can have both. And this one example, you can have this kind of DOS plotted. So one phenomena you probably wanted to know at least the basic mechanism. So say you have D waves like this, D waves like this, D wave like this, and then probably eventually fret up like this. And so this is, you can have D wave cloud, at certain height, as long as it's above the local LCL. Then you can have, you can cloud here, you can have cloud here, cloud here. If this amplitude is large, then what happens is you can have this recirculation. In vertical domain, you can have recirculation like this. And this is called rotor. In, I think, 2006, there is a field experiment in the States, around the Sierra Nevada, and it's called the T-Rex. It's called the terrain-induced rotor experiment. Terrain-induced rotor experiment, and I have that. It's called here. It's called here. terrain-induced rotor experiment. Okay, and you can probably search for it. You'll find it. Okay, and so when your flow comes here, this can separate. Okay, this part go this way, this part go this way. Okay, and sometimes when you have that, okay, and you can have also, this is two-dimensional. You can have three-dimensional too, like this. Okay, you can flow comes in. If wind speed is weak, mountain is high. Okay, then flow probably cannot go, will come back, return. Okay, that's called swamp blocking. And then return flow. And then that return flow can bump into the basic flow, and at a certain point will be U will be equal to 0. The return flow can bump into the basic flow to a certain point will become 0. And that's called the synchronization point. Okay. And here, because it cannot go over, so you will go around. That's called flow separation. Okay, we got flow separation. Okay, and that's called boundary layer separation. And boundary layer separation can be horizontal, can be vertical. Okay. So here you can see, and then you can have severe downstream wind coming down, and then to here and come up, and then you have daughter here, okay. And here you can have severe downstream wind. So then, oh, that's good. We finish chapter. I don't know why this kind of name is not right. Okay, yeah, I don't know why. This is chapter 7, right? Is it chapter 7? Okay. So then chapter 8. Chapter 8, we are going to talk about. Let's see. Oh, chapter 8, we are going to talk about nonlinear flow over mountains. Okay. Okay. So we go step by step. Okay. We go step by step. We have flow over sinusoidal mountain, and then flow over kind of localized, okay, isolated mountain, and then we talk about when we have what happened if we have non-constant scalar parameter L square. Okay, what happened? Then we can have kind of D waves, and then next we are going to talk about what happened if we have nonlinearity. Come back, we cannot ignore it. What happened? And that we produce severe downstream wind. Okay, and then we'll talk about tomorrow. I try. Okay, I try tomorrow. Okay, yeah, try tomorrow. If tomorrow, let me see. Tomorrow, if tomorrow if I can have whole morning, okay, then that will probably make up some kind of part, because we do have to speed up a little bit. Okay, so tomorrow I try if I'm kind of fainted, okay, and then just call 119 and then put me back into second floor, okay, yeah, and then people will be free to go, okay. I'm just kidding, okay. I don't think I'm going to faint, okay. Probably I'll be weak, okay, because right now I am prepared for a test, okay, kind of physical test, and then I cannot eat too much, or I cannot eat certain things. I cannot eat fruit. I cannot eat vegetable. I cannot eat the fish. Fish I can, but had to pee. Okay, and I cannot meat. Okay, and okay. So that are the restrictions. Okay, I'm kind of dying. Yeah. Very hungry. Yeah. Okay, so we'll try to speed up. By this today we finish chapter 7. That's good. Okay, that's good thing. Okay, so. Tomorrow I'll try to see if we can finish chapter 8. Okay. And then Thursday we'll try to probably at least start part of or half of the chapter 9. Okay. Yeah, I know. Yeah, right. Yeah. So, okay. So we'll see, and then next week we have 3 days, right? So I probably will reserve maybe at least 1 day, to talk about the precipitation, or 2 days. Okay. Yeah, and so we probably, once we finish DIN 2007 chapter 5, that's our 7, 8, and 9, then we probably have to jump to the auricular precipitation. That's DIN 2007 book, chapter 11. Okay. Yeah. So then we'll probably cover pretty much. Okay. And some detail of the mathematics we probably have to just tell you how to do it. Okay. So you get the idea. Okay. And then this that will give you the background. If you want to do it, you want to read something, you can be independent doing it. Okay. Yeah. Okay, so we'll stop here for today. Okay, thanks. I'll see you tomorrow. Okay.